So, hello. I think everybody is now here, and I'm sorry for the previous miscommunications, during the first lecture, but it is recorded and you can find it on the my model, and I recommend to follow it. But now I repeat the first lecture in 10 minutes, but of course it's not. It is just to help people who did not follow the first lecture to follow the second one. But you need to go through the first one because there are much more details. Now, there is also one book with exercises. And of course, there are too many exercises. And I shall send you after this lecture email with the list of the numbers of exercises for first lecture, exercises for second lecture, and so on. In principle, I don't press you to solve them. It is your training, your own training. And exercises have solutions. So your strategy, try to solve. If you cannot solve, look to solution. In 3 weeks, I hope that course would be there are in fact 2 courses. I'm not so happy when I have seen the program of this course because there are in fact 2 very different courses. One is complex analysis. It's by itself very complicated course. And the second is Fourier analysis. But we should do as it is done in program. In 3 weeks, we plan to go more or less through complex analysis, and then it will be pre-examination, which is optional. It will be at home, your home examination, but you will get your own problems. I am thinking how to do this, but I will manage this. So everybody will get his own problems. If you pass no more or less this pre-examination, then on usual exam you will not get maybe you would not need to solve 1 or 2 problems related to complex analysis. So your usual examination would be shorter. What else? And after this we shall start Fourier analysis, and maybe next week I also put material which I will use for Fourier analysis. Okay, so then on web page on my model, there are many lectures of previous teacher Joachim Toft, and you can use them as complementary material, but especially for engineering students, they may be not so useful because they are pure mathematical, and there are too many mathematical details which are maybe not useful. But mathematicians can go through these lectures as supplementary material. Okay, so the book is Complex Analysis, and you can take it and even download. I downloaded it to my computer from the library. And what is about complex numbers? Yes. What is my plan? My plan is to go through first 5 chapters, as I told. And we stop, but maybe, I hope, if Fourier analysis would be not so long, I hope that I would come to the chapter 6, which is the most interesting for mathematicians, but multivariate functions, but maybe not for engineers. Of course, as it is 2 different groups of people and engineers, people in technical mathematics, they would get separate exam. It would be less theoretical. No, I also managed to. So the course, from my viewpoint, is the most terribly planned. This is the course for engineers and non-engineers, the course on distance students and physical students, and all this in one packet. But we manage this, don't afraid. Okay, so first 5 chapters, complex analysis. Since complex numbers were so long ago, first lecture was essentially devoted to repeat what is a complex number. And complex number, it's such, given by equation y5, it is such, I can say, formal expression where I is additional element which has only one property, I square is equal minus 1. So it is ideal element, yeah? Now, if you see this picture, two coordinates, x and y, then of course you immediately have the image of coordinate plane, the image of coordinate plane. So with coordinates x and y. Question about book. No, let us do this at the end. Maybe I stop and then I mean in between you can write your question by chat. It is. So the book is not copied. No, maybe I got it from another open source. Then we shall solve this problem. Right. If you have the problem to get your own PDF file of book. So this is this number, and this number is in fact maybe I got it from some open internet. I don't know. I forgot. So we go now to the complex plane. And this complex plane is our usual plane with, x is call it a real part of complex number, y is called imaginary part. And so this was what I wanted to tell. Two coordinates, it's a point on the plane, and we can find the radius, and we can find the angle. The radius is called, this is square root of x squared plus y squared. It's called the absolute value of module of complex number, and theta, which is measured from real axis in anti-clockwise direction, is called argument. So conjugate complex number is here is just minus. The main property of this operation is if we apply it 2 times, we again get the same number. So this is those who studied algebra, it is interesting operation. How it looks geometrically? It is if this is z star is just angle is changed to minus. And in majority of books, people never use star. So this is, I think, a bit, maybe in engineering they use, but even in physics, typically use bar. Z and over Z is bar. So otherwise you would be surprised by other books. Example 2.1, don't try to consider because complex logarithm is very complex function. So go further, modulus, argument. How to find argument? We can easily find tangents of this theta. It is x divided, y divided by x. So algebraic operations, they are very simple. You just write these expressions and open brackets and collect O with I and O without I. And if you multiply, no, geometrically you can illustrate, but we never use this. If you multiply, you just open the brackets, and I square is equal -1. What is more complex, but it's you should learn once in your life, how to divide two complex numbers. So this is this expression. So your aim is to write this in the form some real number plus I multiplied by another real number. But the problem is that I is here in denominator. How to struggle with this I? We multiply denominator by complex conjugate. And we know that z star is equal to square of absolute value or module. So I disappeared from denominator. So now we can write our number with this real part and with this imaginary part. Go polar form. It is very important when you will try to get roots from complex number. And square roots, cubic roots, and so on from complex numbers, it is one of the what you should do on exam. So this without this, you cannot pass this exam. So this is Cartesian representation of complex number. Now we can write polar coordinates. So has this form. We put x and y, and if, of course, this is the sum of these squares is 1. So if R is equal to 1, all these numbers are on the unit circle. So if the radius is 1, so all complex numbers of this form are on the unit circle. So we can write numbers on the unit circle in this form, and theta is going from 0 to pi. Then there's some motivation, but I don't like this motivation. We go directly to this formula 227, and please memorize it for whole your life, both mathematicians and engineers, because this formula is very much used even in people who do some engineering, physics, and so on. This is so-called Euler formula. So it is surprising that the author of this book did not write this. And this is just by definition. So this cosinus plus I sinus, let us write in this formal form. Then we shall see that by using Taylor series, it can be proven, but for the moment, it is just definition. So any complex number can be written as its absolute value or modulus, exponent I theta. So this is exponential form or complex number, exponential form of complex number. This is very useful, very useful. So what you should memorize from the previous what I taught, this is Euler formula, and this is exponential representation of complex numbers. Conjugate is minus. Again, not struggle with logarithm, not please struggle with logarithm. We will be back to logarithm later. This is also Moivre. What is this example with Moivre's theorem? That many things in real analysis can be proved with complex analysis. You do something in complex analysis and then get some equality, and they take real part from both sides, and you will get something for real analysis. Yeah, this formula, and if you have this, and conjugate is just minus, so it's minus here, so minus here, so plus here, plus here. Now, these are two system of two equations for cosinus. We find cosinus. This is system of two equations for sinus, and we find sinus. These formulas you also should remember, because otherwise it's difficult to work. So cosinus, this is usual theta. There is no complex analysis. Your usual cosinus that you know from school can be represented in this complex form as the sum of two complex exponents divided by 2. Your usual sinus also can be represented in the complex form. These formulas are used very much in electrical engineering and wireless communication, because it is easy to work with exponents than with trigonometric functions. It is easy to multiply exponents, but the product, of course, you can also write what is the product of two cosinus. But yeah, so also try to remember this formula. So Euler formula and formula cosinus, sinus. Tangents may be not so useful. You can, now, we can also connect usual hyperbolic functions, get the representation as, so trigonometric functions, cosinus and sinus, in fact, can be represented as hyperbolic functions. So cosinus I W is hyperbolic cosinus W. So no, you can just go through this, but it's interesting that hyperbolic geometry is complex trigonometric geometry. Here we coming to, if you know, maybe special relativity theory and so on. In special relativity theory, its main is so-called Lobachevsky geometry, and main functions are hyperbolic. But if you in some way extend to complex plane, you will get usual Euclidean geometry, yeah? Roots of unity. So this is also you should earn in this course. So we want to take the all possible roots of 1. So how we do? Here is one trick which you also should remember forever. Number 1, with these coordinates axes, and number 1 is on the real line in positive direction 1. But then we can rotate. If we make rotation for 2 pi, we again come to the same one. Again 2 pi, again the same one. So exponent, or if you start rotations in different directions, we again do the same. So exponent plus minus 2 pi ik, it is 1. Then when we want to take the root, for example, of degree n, we just write this formula, write this, and use Euler formula. Then you can calculate. Now, even if you don't know precisely cosinus and sinus, you can do this on computer, on calculator. So approximately you can find the roots for any n, The same with roots from -1. Cubic roots, it's the same. There are many examples, so they were considered during the first lecture. Electrical circuits, I cannot tell you. Maybe if you have some electrical engineering, they will use complex numbers for this. There are also problems, but I prefer textbook, which I will send you. Now we go to functions. We go quickly to functions. What is timing? Oh, timing is take too much time. So now we go quicker. So we consider function of complex variable with complex values. And now we want to define its derivative. Derivative is defined in usual way because we can divide by delta z. So we write this and take limit. A limit means that absolute value, no modulo of delta z, goes to 0. The main trick is that this z has two parameters, x and y. And this limit is when both them go to 0, delta x go to 0 and delta y go to 0. So we can write in this way or in this way, and we should get the same result. So then we get two different. If we get in this way, we get this partial derivative. If we go in other way, so this is we go to limit over horizontal line. This is over vertical line, and we get two different answers. But we want, and this is key point, that this limit exists, it's the same, that it's the same limit. So they should be equal. This expressed in this way, and this expressed in this way, they should be equal. So 3, 4, it is one of the most important equations of the course. This is Cauchy-Riemann equation. So this equation is how to get existence of complex derivative from usual partial derivatives. So this is Cauchy-Riemann equality. Remember it's also. Now, not only z is two variable. F is also complex function. So it has a real part and it has imaginary part. Now we can put this expression in our Cauchy-Riemann equation. So this is def dx and this is the f dy. And now we should collect all with I and without I. And now we get Cauchy-Riemann equations in completely real form, Cauchy-Riemann equations. Then sometimes in engineering, in physics, people use Cauchy-Riemann equations and polar coordinates. There are some calculations. No, you can go through them. We haven't did this for last lecture, but you need not memorize this. It's, yeah. So Cauchy-Riemann equations can be used to understand whether a function is analytic or not. So we find df dx and minus I df dy, and it should be the same. So this function is analytic. This is also, you should remember this, technical approach. So if you want to prove, I write you some function which is function of x and y without z. And I ask, is this function analytical or not? So you can use Cauchy-Riemann equations and check this. So we go. Harmonic functions we get in the following way. we had this Cauchy-Riemann equations in the real form. And now we take here derivative, differentiate this equation by dx. So it would be second derivative of u. And this with the dy, second derivative of du dy. And here will be mixed derivative. Here is first dy, then dx, and this vice versa. And they have different signs. So we get the following formula. It is important for those who work in applications. So this equal to 0 and this equal to 0. So we get so-called Laplace operator. I think you will have the course of partial differential equations or had it. So this operator is called Laplace. It's typically denoted delta, but here they used nabla operator. Nabla operator is dx dy, and this is scalar product of nabla. So we get these equations, and these are Laplace equations. So these are very important equations in physics and for electrical charge and so on and so on. So you should remember that if you have analytic function and take its real u and imaginary part, both these functions are analytic functions, satisfy Laplace equation. And functions which satisfy Laplace equation are called harmonic functions. So you should remember the words harmonic functions as those functions which satisfy Laplace equation. And these functions we can easily get from any analytic function. So, because we have Cauchy-Riemann equation, it's connected imaginary part and real part. It is clear that if you know one of them, for example, real part, by integrating equation, we can get imaginary part. So this formula, where x is considered as frozen parameter, and only dy is integration variable. Constant of integration also depends on x. So there is some long calculation of this constant. You can go through this, but it would not be on exam. In principle, I have never seen that people do this in applications, but maybe in physics somewhere they do. So you only should remember that because there is Cauchy-Riemann equation, real and imaginary part of analytic function are related, and if you know one of them, by integrating equation, we can find another. Yeah, so this is, they apply this. Oh, now we are going to really interesting. We go to integrals of analytical function, of any function of variable z. First of all, how this integral over some curve or trajectory going, this is point z1, this is point z2, how defined this integral over this trajectory? So definition is the following. We should introduce some parameterization, some parameter t. So for x function of t, y function of t, t is between some t1 and t2. Then we can find dz, which is in fact, and then this integral is equal integral usual Riemann integral as you used in your course from t1 to t2 into, instead of z we put its parameterization. Here is z prime derivative of z dt. So this integral over trajectory in complex plane, it is just usual Riemann integral corresponding parameterization. What is the main interest of physicists, of people in doing some applications? They're interested in functions such that this integral from point z1 to point z2. What you should never consider, of course, in your course you would not do this, but if you work in some and do some complex problems in physics or engineering, you should not apply this theory for curves, for trajectories with self-intersection. Here is everything is very difficult. So trajectory should go in this way, no such curves, yeah? was just remark, So people are interested in integrals which do not depend on the curve. So this integral with respect to this is the same as integral with respect to this. Then we go for this long curve and so on and go again to Z2. We are interested when this integral is the same. When this integral is the same. So what does it mean that integral, or that integral is the same? It means that if we integrate over C1, for example, this is this curve, and then integrate over this curve C2, then the difference of these integrals is 0. The difference of this integral is 0. Here is very important remark. Here is important remark that if we go this way or this way, so from Z1 to Z2, or other way around, from Z2 to Z1, integral change the sign. No, because finally it's here is dt. Here is dt. And if we change the direction and also we change the limits of integration, and so it would be it would be just the difference of signs. So integral from Z1 to Z2 minus integral Z1, Z2 is 0, or integral Z1. This formula 342b will be used many times during the course. So if you take integral from Z1 to Z2 and integral Z1 to Z2 again, so the same direction. So we go here and we go here. So it is the sum of them is 0. The sum of them is 0. Oh, okay, they had a better picture. So this is this contour, and this is this contour. So there is this contour. So we go this direction, for example, counterclockwise, and from Z2 for Z1, we go this direction, another. So then this integral is 0. So we, for the moment, we don't know when it happened. We are only, and it was historical development. People in mathematics, they told, who are these functions f, z? Such integrals, or this can be reformulated as integral over closed curve or contour is 0. This equation. Who are these functions? What are these functions? Which are integral over closed curve is contour is 0. So they are interested in this. It was historical interest. And then we're coming to one recollection from your usual course of multivariable analysis. At least I got from Joachim Toft that mathematics students had green formula. I did not get confirmation from Karolov about engineering students, but I suspect that you also should have this in multivariable analysis. What tells this formula? We have some contour, closed curve, and we have some R here is the region inside this curve, So green formula gives possibility to represent integral over curve as integral over region, or other way around, maybe more interesting for physicists. There is integral over some area, this integral, it is the same as integral over the curve. So over the boundary of this area, So if you go to the previous page, we have this curve, and we have this region inside this curve. So green formula tells us the integral over region of special combination of functions is the same as integral over this curve. Yeah. What is this combination? So if we integrate over curve this function, this it's called a differential form, but it's more or less here is x function of t and y function of t, and we put into g and h these functions and integrate, write dt, write derivatives of parameterization, write this integral. It is the same as usual integral dx dy over this area. of this form, is minus and such derivatives. What people did, they thought, let us take our integral for complex function. So there is this and this, so a real part. And there is, because z is x dx plus I dy, so this you will get when you put z, which is a complex number, and u and f, which is the sum u plus iv, and you get this. So this is equal to 0. So now what we have this differential form. It should be this side. Here was the break of a previous lecture. So now we repeat this in more details. Unfortunately, connection was very bad, and yeah. So we have this form. It should be identified with this. Should be identified with this. Then we write this. Then we write this. And now suppose our function is analytic. Our function is analytic. Then we apply Cauchy-Riemann condition, and we get this 0. So the condition which was our dream was to find condition on f when integral over closed contour is 0. We found that if function is analytic in some region, so it should be analytic everywhere here in this region. So for example, if it is not analytic in some point here inside, it does not work. For example, suppose this is center of this circle is some point z0, and our function is 1 divided by z minus z0. So it's in this singularity in point z0, it is infinity. It would not work, yeah? So function should be analytic everywhere inside. Then we get application of Green formula, and by using this Cauchy-Riemann equality, we get that this integral is really 0. So this is the first part of this. I can call it, how it's called, this theorem. Cauchy-Riemann theorem, we can call this, yeah. That for analytic function, integral over closed curve is always 0. If function is analytic, everywhere, if there is at least one singular point, it does not work, then integral of the closed curve is 0. Other way around, suppose that integral over closed curve is 0 for any closed curve. Then we can take fixed point inside this domain R and make curve smaller, smaller, and smaller. It is always 0. So integral of this form of this function would be 0 on any area. Now, I don't know whether you proved in your usual course of analysis that if you have function of 2 variables, or let us, for the beginning, function of 1 variable, and we know that its integral is 0, take some fixed point, and it's 0 on any neighborhood, on any small interval around this point. Then this function is 0 in this point. So the same is done here. There is function of 2 variables, this block, function of 2 variables, and it is 0. Its integral is 0 on any area around any point, because this integral is 0. So then it should be equal to 0. So if we got other way around, so we got that if our function has this property, that integral over any contour is 0, then we get that this is integrand 0. So we get Cauchy-Riemann equality, and we get that function is analytic. Unfortunately, Cohen did not formulate this as theorem, but maybe you can make notes that we proved such theorem. If you have function, any function of complex variable, and its integral over any closed contour is 0, if and only if this function is analytic inside this contour, no, inside some domain, yeah? So analyticity is equivalent to the condition that integral over any closed contour is 0. Analyticity is equivalent to the condition that integral over any closed contour is 0. Yeah, so we prove this. It is one of the theorems of I think it will be even on exam. It's very good theorem, and you also should recall Green's theorem. Green's theorem. On the exam, of course, you could use notes. It's maybe looks strange for people, but my aim is not that you memorize, but you should have the picture of the proof. And I'm very clever to make the question in this way that you should understand the proof. I would formulate, I would not tell just copy the proof of this theorem. I would ask you something about the proof, yeah? So good. Now this example. So, no, for example, we have function z square. Z square is, of course, analytic because we can calculate its derivative as just usual function. So maybe it is good place to make remark that, of course, you can check Cauchy-Riemann condition, but it is good to do when your function is written as function of x and y. But if function already written as function of z, of course, you can make derivative if you typically do. So z squared derivative is 2z, zn derivative, and so on. So if function already written as a function of single variable z, you can differentiate it as you did with usual variables, yeah? So now we consider three contours. So we go from 0 to 1, and then we go to point up. We go to point 1 plus I. It's good to remember that if you have coordinate axis, the point 1 is here, the point I is here, the point minus I is here, the point minus 1 is here, yeah? So this is contour from 1, this is x coordinate, and plus I, this is y coordinate. Another contour, this is not contour or pathway, yeah? Or this pathway. I would not go through this. He is very in details written how they calculate these integrals. And you will see that integrals are really the same. So they do not depend on trajectory. Yeah, this is more or less that I wanted to tell you that if function is analytic, then the integral between z1 and z2 does not depend on trajectory. So it does not depend on parameterization. You even need not to think about parameterization in many cases, sometimes, but in many cases. And you should do the same as you did in real analysis. So, for example, you can find differential of our function df in this form. Suppose we have this function, which is derivative of f, yeah? And then you use this formula of integration. So if you have df and gz is its derivative, you can use this formula. Oh, yeah, if it's df, yeah, so there is f as z2 minus fz1. As you did in your first course of real analysis of one variable. So, for example, if you want to integrate Zn and so on. Now we go to singularities. So the life is not so good, and we have many functions. which have problems in some points, which are not analytic. For example, consider function 1 over z. No, they represent it in x and y, but we don't need this. It is clear that in the point z equals 0, this function goes to infinity. It's not defined. So this function is not analytic in the point z equals 0. So, but so this function has singularity. So it's the example, if function is not defined in some point, it has singularity. Now we consider the following type of singularities. Consider derivative of our function of some degree k, and suppose that the limit singularity in the point z0. Suppose that limit of this derivative is infinity. So here is very good situation. Here is immediately function by itself. So derivative of the order 0 goes to infinity. Yeah. But maybe, and we shall consider on the next page example, it can happen that function by itself does not go to infinity at the point z0, but some of its derivative go to 0. So suppose that there exists such case that derivative of order k is not defined at the point 0. So then this is singularity corresponding to this degree k. The basic example, consider z in the fractional degree 3 divided by 2. 3 divided by 2. Of course, it is well defined at z equals 0, but up to multivalued functions, but we shall not consider this now. First derivative, it is square root, is also finite at z0, but second derivative, now square root goes to denominator, is infinite. So this is this function, which is by itself well defined, it still has singularity in the point 0, because derivative of order k equal to is goes to infinity, is going to infinity, is going to infinity. Now we give formal definition. Suppose that we have such function which has singularity, that this derivative go to infinity, but we can multiply this derivative by, in the point z0, but z minus z0 in some degree p, and p is real number. So for example, it can be 3/2, 5 divided by 2, and so on. So they exist, but typically it would be just natural number, either 1 or 2, and so on. In our course, it would be always natural number. But general definition, p is any real number. So if we can find such p, that we multiply this derivative by z minus z0 in degree p, and then it would be not infinity, then our function is called, the singularity is called removable. Some people tell non-essential singularity. But if there is no such p, so we have this derivative, it goes to infinity, but we multiply it by z minus z in any degree, and it still goes to infinity or not well defined, then it is non-removable. I suspect that majority of our course would be about removable singularities. If we will have time later, we will consider non-removable or essential. In fact, it's not so much to do with these singularities. They are non-removable. So what is the idea? That here we multiply by this and singularity disappear. It is removed. But it can be that it's impossible to remove it in this way. So we go to our previous example. Z in the degree 3/2. No, first derivative is at 0, and we found it is then the second derivative, as we discussed, it is square root, and it is infinity. But if you multiply this by 1/2 and consider limit to 0, it is not in infinity, and so on. So singularity is removable. But now coming the question, this we will see later. So we multiply by z1/2, it is already not infinity, but we can multiply by z3/2, it is non-infinity. It's good to determine some degree, some value of p, which is the most important. It is natural to take this minimal, so that this we shall do formal definition a bit later. So this is already, this is okay. We multiply by this, and we get not infinity. We need not the second two equations. Now we're going to exponential function. 1 exponent 1 divided by z. And it is non-removable, singularity. In principle, even I did not meet any other example beside this. Of course, here could stay 1 divided by z square, but z10, but all these non-removable examples are based on this exponent. No, maybe I should refresh and find some more other examples, but all textbooks contain this example. So here is some calculations which no, maybe we do not need do them. I think we can do simply. We can do simply. Take this function, exponent 1 divided by z. Take its derivative. Take its derivative. So what would be derivative? Minus exponent and divided by z square. So it goes to infinity. For z goes to 0. Yeah. So this is this singularity. This singularity. Because if we take derivative, derivative goes to 0. The derivative goes to infinity. Derivatives go to infinity. Now, if we multiply this derivative by any degree of z, we would not save the situation, because when we start to differentiate, we will get the same. So it is meaningless to multiply exponent 1 divided by z in any degree. We still would not remove the singularity. So this is non-removable singularity. Yeah. So now we maybe make break because we're going to the pole. Pole, this is the main example and the simplest example of singularity. On one hand, it's simplest. On another hand, this example is people everywhere use only poles in applications. So now I suggest just maybe 5 minutes break. 5 minutes break. So we continue. There was a question, very good question. Is Cauchy-Riemann condition equivalent to analyticity? No, for infinitely differentiable functions. And this question was discussed in the first lecture. I suggest you to go to the first lecture. And what I have not repeat in this second lecture is the notion of entire analytic function. This is function which is analytic everywhere. So, okay. So now we go to this type of singularities. Pole singularity. Suppose that already function by itself goes to infinity at the point when z go to z0. So if this function go to infinity, for example, function 1 over z, function 1 over z. So the basic examples of such functions is 1 over z, or for example, in the point z0, 1 over z minus z0. So this function go to infinity in this point. We can I use the LaTeX notations. This is, for example, in the degree, in some degree n, yeah? For example, this function, 1 divided by z minus z0 in the degree n. So this function, of course, go to infinity at this point, but we suspect, and it's clear, that if you multiply it by z, for example, this, let zn be n large to make consistent notations. So now if you go to the next formula, we have that, consider this function. It is natural to consider this function multiplied to, the idea is in some way to remove singularity by multiplication by z minus z0 in some degree n. So this is our business in future. Yeah? So now this function would be analytic. Suppose that we have such function, but they exist. No, here it's evident, but generally it can be very complicated function. Suppose that this function already has this property, that this limit is not zero. So in our case, we just multiply it by z minus z0, and we get that limit would be 1. It would be 1, not 0. If here we put some number, a, then the limit would be a. So this limit is of very big importance in following considerations. So pole singularity has the following, its singularity of the following class. Limit is infinity, but we can find z minus z0 in some degree n, such that this limit is not zero. Finite non-zero complex number, pole of the order n in this pole z, and this factor removes this pole. Let us start in further considerations, maybe until the end of this lecture. We shall consider the simplest poles, when it is enough to multiply just by z minus z0. So the pole of the first order, or simple pole. Yeah. Okay, so this limit, which was considered on the page before, it's called residue. The notion of residue you should remember. You have the pole of degree, you have the pole of degree of the first order, or simple pole, and then to remove this pole, it's enough to multiply by z minus z0, and then this limit, our function, it is already non-zero. It is called residue of the pole, or simply residue. This is called residue of function in the point z0. So remember the word residue. Typically people tell not residue of the pole, but of function, but no problem. Okay, so now we go to our function 1 over z, And it is clear that it's the pole of the first order. And how to remove it? Multiply by z. So this is just 1. So residue at the point z0 of this function, which is singularity, z0 is singularity, is equal 1. Now they go to this function. Of course, this is no, it's more. We can look to limits, but it's clear that just it's better to have heuristics. We understand that this pole is of the degree 3. If we multiply by z cube, we get sinus 1, and it is non-zero. And so this is the pole of degree 3. Now, for example, this function. No, they use some long discussion, but I suggest do this again heuristically, and you can do this on exam. Sinus z. A bit later, we shall study Taylor series for analytic functions. So it is more or less the same as for real functions. So sinus z is approximately z. So one z disappear. So this function is in the neighborhood of 0 is 1 over z square. So our pole is of the second order. Yeah. Yeah, finally they wrote this near 0, it is this, so the pole of the second order. Okay, now we go to also one of the main theorems of complex analysis. This is theorem how to calculate integral around singularities by using residues. So it would be done the following trick. Instead of calculation of integral, which can be very complex if you make parameterization and try to calculate this in usual way, we will just calculate residue. Here is the good place to make the following remark related to the previous part. We proved that integral f z dz of analytic function is equal to 0 for any closed contour. Good. Now, here I had this course maybe 30 years or 40 years ago for engineers in Moscow. And we showed, it will be even in your pre-exam and in your home task. This is good, good example to demonstrate that at least at that time, maybe now computers became better. At that time, it was possible to demonstrate superiority of human brain over computer or even supercomputer and so on. Suppose we write integral of some very complex function, of some very complex analytic function, big expression. I will send you this example during this pre-exam. Everybody will get your own function. For example, z in the degree 1 million, cosinus z plus 3 in the degree 10 millions, and so on, and very big expression. And then integrate over unit circle. So parameterization for unit circle is very simple. This is r radius multiplied by exponent e phi. So when you put this parameterization, you will get usual integral from 0 to 2 pi And at least 30, 40 years ago, if you put it in computer, it would be never 0. There will be so many computational, no, not mistakes, but imprecisions that answer could be even very far from 0. But you know, your brain knows that since function is analytic, integral is 0. Now we go to more interesting situation. And now we consider integrals over contour around some pole, simple pole. So pole which is removed by multiplication by z minus z0. So this is a long theorem. This is long theorem. And I first make jump to conclusion. And then we consider the technical construction because it would be used for many, no, in many other situations, Okay, so we go, and we have the point z0, and this point is pole of the first order. So more or less, this is a kind of function 1 divided by z minus z0, and in the denominator can be some analytic function. We want to integrate over this contour. They make not so good picture because from the very beginning they wrote some circle. Suppose that there is not circle, the main story, but some very complicated contour. What is the first part of the proof? The first part of the proof is that we can reduce integral over the CA. On the picture, it's already a circle, but it can be any contour, any closed curve around the pole. We want to prove that this integral over CA is equal to integral, and here's a picture over any small circle around this point. So we have integral over some curve around z0. The first part of the theorem is to reduce this integral to the integral over small circle around z0. First we jump, Suppose we did this, and now we arrive to this point. So we want now we forget about previous, and now we have the very simple problem. We have the point z0, and we want to calculate our integral over small circle around this point. In the previous part, then we will go back and we show that our integral over any curve around this point z0 is equal to the integral to this small circle. Okay, so how they do this? They make parameterization. So there is the radius of circle. There is the point z0. So this is separate task. We have the point z0, and we want to calculate the integral around this point. And we know that in this point we have the pole of the first order. That means that our function is more or less analytical function divided by z minus z0. So, and they make parameterization. So that if we make shift z0, this circle is just around zero. And around zero, our parameterization is very simple. This is radius rho, which is fixed, and consider it as small, and e theta. So when we go around circle, complex number by using Euler formula can be represented as exponent I theta. So this is this parameterization. This is good to also remember this, how to parameterize unit circle around zero. If circle is shifted, there is this center of the circle z0. Now we find the differential, we differentiate this, we find the derivative, so there is d phi, this one, and we go, so this is integral over this circle, and this is counterclockwise, so there is some, in this book, they use not so good notations, because integral can go this direction or this direction. So this integral they called counterclockwise, and this integral in this direction. They call it clockwise. Typically, in other books, you will find just the following picture. There is integral, there is this circle, and on this circle, there is just arrow in what direction you rotate. Unfortunately, in this book, they write just in words. Here is counterclockwise. So in other books, it would be this circle, and arrow shows that we rotate in this way. So there is arrow showing rotation. Yeah. So if we use this parameterization, that I used, where the angle phi goes from 0 to 2 pi, we goes counterclockwise. So the arrow on this counter is this one. If we write arrow, it would be this one. So we go in this direction. Phi from 0 to 2 pi. If you go other way from 2 pi to 0, it would be this direction, yeah? So we calculate this integral. We want to calculate this integral. So we put dz. dz is d phi. There is z minus z0. We can put phi 0 just 0. It's we always can start our angle from 0. So now what we do? For this integral, it is now usual Riemann integral, nothing from complex analysis. Usual Riemann integral for one variable angle phi, and it goes in the region 2 pi. So now we put the radius to 0. Now we send the radius to 0. Since our function is continuous, everything is continuous, we change the limit and integral. So here is this integral, here is the limit, here is this z minus z0, fz, and this is differential which was on the previous page, I d phi. And now what is this? This without I, if I take away, this limit z minus z0 fz, it is precisely residue of our function at the point z0. So this limit z go to z0, or radius of our circle go to 0, it's precisely residue. So we got, this is the most famous formula of complex analysis, that integral counterclockwise, so in this direction, over this around this point z0. Z0 is the pole of the first order, is equal to pi I residue at this point. 2 pi I residue in this point. No, please at least memorize it. But of course, on the exam, I would not ask you all details of the proof. But I can ask you, what is this? What is schematic? Can you represent schematically what is the formal line of the proof? So first, maybe you can start even with this. Not go as them, but start with this essential technical part. Take this picture. Take this circle, small circle around pole. Make how loop parameterization, find the differential, put into integral, and lucky we have already z minus z0. And in definition of pole of the first order, we have also z minus z0. Then limit rho go to 0. If rho go to 0, if radius go to 0, this z which is on this circle go to z0. So now we get this, and this is residuum, So we got this formula. So, and this formula was phi goes from 0 to 2 pi. This is anti-clockwise or counterclockwise. If we go other direction, we change just the sign. So if you have the same integral clockwise, this is minus 2 pi residue. But now we should make this first part, and first part is a bit technical. So now we have some curve. They wrote the circle, but it can be any curve around this point. And now we would like to prove that this integral over this is equal integral over any small circle around point z0, because at the end of the proof was for small circle. Was for small circle. What we do? We write this this integral, what they call C in, so internal. It is in fact our small circle that we used at the end. Yeah. So we get this small circle. We cut this contour, some hole, and we unify in one circle. So, and directions should be, for example, since here we selected, no, for example, here we selected, this is anti-clockwise, and we go anti-clockwise, counterclockwise, yeah. So direction is the same. Now, we assume that only singularity is in this point. Then in this domain, there is no singularity. So function is analytic. So we can apply this, for example, green formula, or just know that if our function is analytic in this domain, integral over this contour, over this closed, it is closed contour, it's equal to 0. So this integral is 0. And they write this integral by taking into account all pieces. So we take this piece, C out, C internal, and up and down. So the main idea is that this up is go this direction, and this down, when we connect them, they compensate each other. So this block disappear because of these arrows, So, and they do this, they consider situation when gap go to 0. So they make the continuous deformation of our contours. It is still 0, the integral is not changed, it is 0. It is 0 up to the one goes, the gap disappeared, up to gap disappeared. And when gap disappeared, they compensate each other and they disappear. And we get what we dreamed to reduce to what we considered at the beginning, integral over small circle. So this disappeared, and we get that this integral is equal to this integral, They suggest another proof. No, it's good, but maybe it's too complicated. They told that how to close the gap. They thought we make another contour. This contour is also closed. Function is here analytic. So integral is also 0. To this 0 plus this 0, it is still 0. And now we move this inside. Move this inside. And this one, which was from here, compensate this one, 0. This one, which was here, compensate this. So this to disappear, and we again get what we wanted. So the idea is very simple. So we can omit all this writing. So finally, we prove that our integral over a very complex curve is the same as integral over any small circle around our point. So we proved this, one of the main theorems of the course, that if inside this closed circle, which we selected counterclockwise, direction is important, because this is just parameter phi, from 0 to 2 pi, as was in these calculations. It is equal to pi I residue in this point, So for example, and they consider, for example, this example, exponent, yeah, so on, and integral, yeah, and they have some pictures, yeah. So first it is contour around which contains this 2i, so some contour which is around this point 2i is on this axis. So we consider this function. This is pole z minus, this is 2i play the role of z0. the pole of the first order. So our residue theorem is applicable. We write that this integral is equal to pi I, residue in this point. And to find residue, we just multiply this function by this denominator. Denominator disappear. We have only numerator. So it would be exponent put instead of z to I in the degree to I, and sinus iz, it is hyperbolic sinus of 2. Sinus 2iz is hyperbolic sinus of 2. So this is correct. If it is outside, if this contour is this one and 2I is outside, integral is of course 0. Moreover, we don't need consider circle. We can consider, as I told, any contour again around 2I. For example, square, triangle, what we want, any curve. It is still given by the same number, 2pi residue class, residue of this function. If it is 2I outside our contour, then integral is always 0. We can consider here triangle, rectangle, everything. So this is okay, the same. So we have okay. Now it can be many poles. It can be function which have many singularities inside the contour. So for example, it has singularity here, here, point z0, z0 prime. How to modify our theorem? Modification is very simple. Modification is very simple. To this situation, when we have many poles, we still consider poles of the first order, only first order. Higher orders also reduce it to this theorem, but you need a bit more job. But two poles is very simple. We have this contour, here singularity, and here singularity. Here is more or less singularity of the type some analytic function divided by z minus z0. And here is another analytic function divided by z minus z0 prime. So we make small circles around these points, and then we connect these circles with big circle. So we get this and this, this and this. And you see that picture is more or less, each local picture is more or less as it was at the beginning. So here these two trajectories, this is go this direction. We again go counterclockwise, 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 counterclockwise. So again, the idea is to move this to this gap. We want to make 0, and then when gap is 0, this compensate this compensate this, and then what we will get, that integral over this open contour will be the sum of these two integrals over small circles. But integrals over small circles, we can calculate. And finally, if you omit, we need not repeat parameterization and so on. Again, you should just remember this formula. That if you have, for example, two poles inside some contour, and then to calculate this integral counterclockwise, so in this direction, counterclockwise, it would be residue in this point plus residue in another point. If it is clockwise, it would be minus sign. If there are many poles, so for example, we have closed contour and poles z1, z2, zn, so they are enclosed by this contour, then this theorem tells us that integral over this contour counterclockwise is equal to pi I and the sum of residues in these points. So this integral can be as complex as you can imagine. But residues, it's quite easily to calculate. It's multiplied our function by z minus zk and find the limit. Typically it is easy to find. So this part is easy to calculate. This part is difficult to calculate. So if function is extremely complex and you use some parameterization even over circle, it can take maybe it's very interesting for me really check for usual computer how much time it would take to calculate the complex integral and whether it would be equal to this. Yeah. So yeah, if it is clockwise, it is here minus. It is here minus. Uh, Clockwise, counterclockwise, the whole your intuition is for circle because everything is reduced to circles. So all your intuition is counterclockwise. It's more or less natural interpretation is counterclockwise. So here we go, angle is going from 0 to 2 pi. I remember when I was at university, finally I observed that I walk around the big building of Moscow State University always counterclockwise, always counterclockwise. So I learned so much that it is right direction. Now, consider example. So we have what type like Cauchy residual class theorem for a function which has two poles, simple poles. We are still in simple poles. It would be not so big modification for non-simple poles. What is the difference? If pole is non-simple, then we multiply derivative of some degree by z minus z0 in the degree n. For the moment, poles are simple. For example, this function. It is also a good example to understand that what is z square plus 1. It can be written in the usual way, da? So it can be written as z square plus 1. It is equal z plus I, z plus I, z minus I. No, because I multiplied by minus I is 1. So this is good formula. This is good formula to remember, da? And use it always. Yeah, so now we have these two roots of these are two roots. These are two conjugated roots of 1. So we know that in complex, those who will follow first lecture, you will understand that there are many roots from 1 now, da? In many roots, for effects are roots from -1. These are roots from -1. Yeah, so these are two roots from -1. And if you have contour around them, this is the sum of two residues. This is the sum of two residues. This one and this one. And our function has this form. We expand denominator in the product. How to find residue? We multiplied in the point I. We multiplied by z minus I of this function. This disappears with this. And now we put I in the rest. This is e exponent in degree I divided by 2I. In the same way, we can find residue in the point minus I. Here z minus I, z plus I. We get this. So the integral is equal to the sum of these two integrals. And look what we have here. I minus I divided by 2I. We can recall the beginning of the lecture that we prove that it is sinus 1. Because sinus theta is given, what is sinus theta? Sinus theta is equal exponent I theta minus. It is also good to remember minus I theta and divided by 2I. So this is sinus 1. If you, and they also want to demonstrate in this example, that if we go, that you always should check very carefully what points of singularity are inside the contour. For example, if you get the problem to find, for example, this integral, why it's go this direction, we can close in this direction, I think. Why it's written in this way, it's not clear. I would like to write in this way, so it is closed. Or they use this for they illustrate this, that this contour can be from these two contours. I would like just to tell you, if you consider such contour with arrow in this direction, it would be just residue here. I think they just, yeah, you should, yeah, so, and in this, it is residue here. So it is, yeah, so, then our next topic during our next lecture, would be Cauchy residue theorem for high order poles. So the pole which has high order, says there is a question: are pole singularities related to the order of growth of Fz? No, they are related. They, of course, they give our order of growth Fz. When z is approaching point z0, because singularities are local notion. Yeah, singularity is a local notion. Singularity is how function really grows around the point z0, and we consider very special class of growth, polynomial growth, да? When our function can grow as z minus z нулевое, z0 in some degree n. So pole singularities give us the degree of growth of our function when we approach point 0, but only for such class of functions which have polynomial growth. If growth is not polynomial, then it is not pole. Of course, the most interesting story is this function, exponent 1 divided by z. But first of all, we cannot integrate it. And maybe because of this, it is never appear in applications. In applications, you have always pole. Poles appear, and because, for example, we have function 1 divided by x square plus 1. For example, consider this integral, dx divided by over real line x square plus 1. It is a well good denominator in real numbers. But in complex numbers, this x squared plus 1 is what we consider it. It's z squared plus 1. It has already singularities. So we can use this theorem. So what I want to tell that a bit later, we shall use this machinery to calculate usual real integrals. By continuing our function to complex plane, integrating over contour, but then we should have such situation when these complex pieces disappear. So now we finish. Unfortunately, next Monday I cannot give lecture because I would be traveling. Back to Warsaw from Belgrade. And next lecture will be in 1 week. It will be, this next lecture will be both Zoom, and I also would record it. And also in classroom. Now, in classroom, we can try to make some experiments with whiteboard, maybe put computer in front of it and write some formulas, but I'm not sure how much I succeed, yeah? What is about today? Today I will send you email with problems, from this book of exercises that I recommend you to. Yeah. I shall send you these exercises that should be done. And the book, which book is most important regarding exercises? On the in the blog materials for the course, there is some book which is called Exercises with Solutions. I will copy its title in the email. And I also write Lecture 1. I recommend to solve problem 1579. Lecture 2. I recommend to solve problem 4, 6, and so on. It's again more or less for your usual training. Of course, if you have more time, you can look to other problems. This book, which I want to recommend you, is good because it has solutions. But of course, try to solve without looking to solutions. You can do as we did maybe in school. You put a piece of paper and you don't see the solution, see only formulation, try to solve it. If in few hours, few minutes, you are not able, then you can look to solution. No, maybe it's even good to look to the first problem solution, second problem solution, and they are more or less similar. Yeah. Okay, so I hope that we shall proceed in this way, and just wait my mail. Okay, next week I will send you the link which would be working for all lectures. Since next Wednesday, there will be the same Zoom link which will work for, and lectures will be on Mondays and Wednesdays. And if near the end of February, I shall see that I am not in time. Then maybe we shall add more lectures. Yeah, so the course is very big, and we should select what you should know. Because, of course, I can put to you so much information that finally you will not remember anything. So for today is everything okay. So thank you very much and bye-bye. Now stop share. So stop
Can
share.
I ask my question about the book now?
What is your question?
Yeah, I ordered the book that was in the syllabus.
Mm-hmm.
And it was this one, and it seems to be a different book.
It is the same author, not?
No, it's another author. It's Edward B. Saff and Arthur David Schneider.
Maybe there are few different groups, and maybe in another syllabus is another book.
Yeah.
No, I think it's not bad, but you just spent money. This problem.
Yes.
Yeah.
Can I so I should send this one back and order the other one that you have?
If you can do this, it would be better. Yeah.
Okay. Thank you.
If you are able to do this, yeah. Okay, thank you. Yeah. Thank you.
Sorry, I have another question.
Yeah.
Regarding the pre-examination that you mentioned in the beginning of the dictation. How can we prepare for it? I mean, could you please just put up some...
The problems will be the same as in this book with exercises. No, not the same, but the modifications. If you solve, for example, now I send you email. For lecture 1, you should solve such problems, yeah? For lecture 2, you should solve these problems. If you solve them, on the pre-examination would be problems, no, there's some another source, another modification of these problems.
Okay, I understand, but the thing is, I did not buy the book yet.
No, everything, no, this book with exercises is in, go to my model. This is section materials, yeah?
Okay.
And at the very end of this section, there is PDF file. It's called Exercises with Solutions. It is a whole book. You just open it and you can copy this file. Moreover, this Cohen book, I think it exists in library. I shall check now again. And my picture that you can have also PDF. Personally, I know it's of course not good habit. I finished to read paper books. I read only from screen, so maybe it's, yeah, you can also need not to buy.
I mean, I'm
Yeah,
sorry.
just I disturb you for a moment. Somebody already wrote me, Lucas, that I found the book as ebook at LNO library. So in principle, you need not buy this book. You go to LNO library and book exists. The book of lectures and the book of exercises exist on my model.
Okay, but when I went through my model, I couldn't find the book. I mean, the exercises book.
Yes.
So you
It
said
exists, at least I have seen it's
It's there.
before
It's
lecture.
there.
Maybe I will write you the title and no, I check, yeah, maybe I check this.
I
There's a
found
lot
it on my
of
model.
material, there's a lot of material of Joachim. What I shall do, maybe now I make it hidden and it will be just my material, but then say in 1 month, I will open also Joachim's material that you can complete your knowledge, yes? Because now it's too much material. Now
okay.
it's too much material, maybe it was just lost, yes? Yeah, okay. So
Okay.
now I finish, yeah?
Uh,
Or another question. If somebody have other questions, yeah.
Sorry, could you just put all the exams of the course, just to know how the final exam would look like?
You will get problems and theoretical problems. No, theoretical problems will be, for example, can you present schematically the derivation of residual theorem? No, it would be more or less the second part, how you calculate the integral over the small circle and take the limit to 0. And maybe you just draw the picture because they wrote in the book too many integrals. Your mind is disturbed by them. You just write this picture and say that when these two contours, this one and this one, go to each other, they disappear and we get this picture. So it would be such answer to this question. Others will be also theoretical, will be practical problems, which are again very similar to problems with the book of exercises.
Okay.
So I don't want to give you an exam something what we have not done. So if you do just at least few exercises for each lecture, you will be, I think, good at exam. Yeah. Yeah.
Thank you so much.
Yeah. Okay. Thank you. Now I try to end the lecture and meeting for all.